Okay, now we are recording. That's October 16, 2024. We are right here in the calendar, in the schedule, and 2 weeks from now, we're going to have our second exam. For now, we have chapters 3 and 4. We're almost over with chapter 4, and hopefully we'll be able to finish chapter 5 before next week. Chapter 5, right? Before next week. If that happens, we're going to have chapter 3, 4, 5. Why did I put chapter 1 here? Okay, I put chapter 1 because of the labs, okay? That's why I put chapter 1 here. Chapter 1, the labs cover some of those labs. And let's go here. Okay, Wednesday 1. I corrected the report of lab 1. Check a PDF file in your group folder. Let's take a look. Group 1. That's your correction right in here. Go ahead, open your PDF file and let me know if you have any questions about the correction. Your grade is in there. It's at the top of the document, but also at the bottom as well. And I tell you exactly where the points came out from. Okay. Group 2. Here you go. Group 2. Here you go. Here is your here is the correction for your lab report, your first lab report. Group 3. There you go. That's the correction of your lab report, the PDF file again. Group 4. Here you go, group 4. Group 5, right here. Group 6. Okay. Oh, yes, I did, Sean. I did upload the notes to Canvas. Let's take a look there. The latest notes, let's see. I recall that I did upload them. Let's take a look. Courses, physics 1, 2. Yeah, that's the one. That's the notes. Let's see. It's a long document. Takes some time to. Let's see here. Yeah, you're right. I didn't upload the notes. Okay, thank you for letting me know. Let me fix that. At least I thought I had done that. And what about the? Let's see. Let upload the notes first, and then we look at the recordings. Okay. That's the notes right in here. Yeah, that's the notes. If I didn't upload the notes, most likely I didn't upload the recordings either. Let's take a look. Home videos, right? Laws of Motion, the 14. Yeah, the recording I uploaded, but I forgot. Apparently, I forgot to. Yeah, here you go. Good. So we're recording now. Yeah, the recording I uploaded, but I didn't upload the notes, right? But now you have it. You have the notes there. Okay, today, let me put here, yeah. When we are done today, I will 2024, 10, 16, right? Motion 4, lab number 3. That's what we're gonna do today. Any other questions? So go ahead, check your corrected lab report and let me know if you have any questions, okay? In this corrected lab report, many of the mistakes you made are highlighted in different colors, okay? If you made a mistake in the units, for instance, if you made a mistake in the units, it will be highlighted. If you made a mistake in any of the cells, let's put it this way, in any of the cells, okay, the respective cell will be highlighted with a determined color. Okay. Each color reflects one type of mistake. Right? Like units, significant figures missing, significant figures added incorrectly, right? CL and others. Let's see. Units, significant figures missing, significant figures added incorrectly, and CL. And the CL, okay? At the bottom, your final grade, here you go. Your grade in the report is displayed at the top of the document. Specifically, yeah, I don't have the cell number here. Okay, so you're going to see at the top of the document grades to the left and the grade and the numeric grade at the right, okay? You're gonna see that. At the bottom of the document, there is a table with the number of points subtracted from your grade, right? If you don't have any mistakes, you got 100%, 100 points. However, if you have any mistakes, I assigned a proper number, the proper number of points, which is subtracted from the highest possible grade. It's a table, okay? So incorrect units, is if you miss any of the units, the incorrect unit is going to be highlighted with red color. If there's any missing significant figures, let me write that down here for you. Uh, the colors of the incorrect values are the following. One, units, red. Missing significant figures, blue. 3, significant figures incorrectly added. Significant figures incorrectly added. That's green. Okay. And what else do we have here? Let's see. Units and CL. CL is like a brown for CL. If your CL is incorrect, kind of a brown. Okay. But then there are others too, like graph optimization, okay? Graph optimization. You have to optimize your graph. It doesn't have a specific color in there. Okay, and everything here that you see here, I wrote a computer program to grade that for me, okay? Everything else that comes after, I have to do that manually, like a graph optimization, graph labels. I just refer to the graph that you put in our spreadsheet and find out whether those you place those are correct or not. Okay, the regression equation, right? You gotta put the regression equation in your graph. The R square, put also that in your graph, and all those are correct manually. So it's all there in your PDF file. Okay. Let's see if we have any more questions. Any questions so far? For today is to trying to understand the concept. Okay, so yes, that's right. We are going to finish chapter 4 today, and that's what I want to pass to you right now is the correction of the lab report. And if you have any questions about the correction of the lab report, just let me know. Okay. And what we have to do, let's get the book first so we can locate ourselves. While plus right here. What I want is this what you see here. Okay. There is nothing much left there in chapter 4 right now. And gravitational, let's see here. That's chapter 4, right in here. Okay. We didn't cover the gravitational force yet. Okay, we did cover Newton's third law of motion. You have to memorize the statement of the problem, right? Here you go. It's it's very important, this concept as well, okay? By the way, when during the beginning of the space program, for instance, there was a a situation that the astronauts faced in low Earth orbit. First, we have the Mercury program to launch just one astronaut in a capsule around the Earth and come back, okay? After the Mercury program, we had the Gemini program in which two astronauts flew inside the spacecraft. There was the case of one of the missions in which one of the astronauts was going to leave the capsule and float outside just to see whether he could function properly or not. Okay, and this is real life. It actually happened. Okay, one of the astronauts he floated outside the capsule while the other astronaut stayed in there. He was tethered by umbilical, so he wouldn't move away from the spacecraft. Okay, and because the astronaut was not familiarized with that zero gravity environment in which he floated in there, he started to panic outside the spacecraft. He spent some time there outside, and at the moment of going back inside the spacecraft, he couldn't make it because he was not familiarized with that zero gravity environment. And he was struggling immensely. He was wasting his own energy and becoming very tired. Okay, this thing really happened, real life. And he tried to get into the spacecraft. He couldn't get it because the moment he would touch the spacecraft, he moved away from the spacecraft. Think about that. You're going to touch the spacecraft, and if you're not familiarized with the zero gravity environment, the moment he touched it again, he would be moving away from the spacecraft, and he would try that several times, okay? Until he finally managed to get inside the spacecraft, and he was completely exhausted when he went back to the spacecraft. And so when those astronauts, they went back to Earth, they were trying to figure out what happened. Why that specific astronaut couldn't get back to into the spacecraft, right? And at this very moment, NASA was considering leaving that guy outside the spacecraft and returning just the other one, because NASA couldn't jeopardize two lives because of one, right? Those guys, when they fly in space, they know that they are risking their lives. And the scientists, after examining the situation, they finally concluded that what was happening there in zero gravity, in low Earth orbit, was that it was Newton's third law of motion that was involved. Okay, think about that. The astronaut would touch the spacecraft. The moment he touched the spacecraft, he's pushing on the spacecraft, right? And the spacecraft was reacting to his push by pulling him away from the spacecraft. That's what was happening. You know, but there is one on the tail. Just knowing that it was Newton's third law of motion that was involved in that incident, which hopefully didn't cost any lives, okay, was not enough. Just by knowing that you have Newton's third law of motion acting in the astronaut, just like this illustration here in the book, okay, it's not enough, because now you have to practice in practice, right? You have to practice this thing. You have to recognize how Newton's third law is going to work on your body, okay? And finally, NASA figured out that the problem was Newton's third law of motion. The astronauts had to get familiarized with the zero gravity environment and use Newton's third law of motion to their advantage, not to their disadvantage, right? So if the guy wants to return to the spacecraft, what he has to do, he cannot touch the surface of the spacecraft alone. He has to grab it and pull the spacecraft towards him, or pull himself towards the spacecraft, okay? That's what NASA start training their astronauts. And if you have the opportunity in the future of flying, NASA has an airplane, okay, that simulates zero gravity, which is the NASA KC-135. So if one day you have the opportunity to fly this airplane, and NASA has programs to fly students in this aircraft. This aircraft is used to train astronauts, by the way, and also to perform zero gravity experiments here on Earth. Okay, you may end up facing this type of situation. Okay, I was fortunate enough to fly on NASA's KC-135. We call it the Vomit Comet, and I faced exactly the same situation when I was inside the aircraft during moments of zero gravity. Okay, I start to move in ways that I didn't expect while I was floating there, and I was getting very tired too because I was going one direction when I want to go in the other direction. Okay, and because I was not familiarized with that environment, I did know about Newton's third law of motion. Okay, I still couldn't control my motions inside that airplane, and that's what I want to pass to you. And it's not that's just one type of application, real life application of Newton's third law. This illustration shows it exactly. Look at this astronaut, right? Instead of going towards the spacecraft, he'll be moving away from the spacecraft. If this astronaut is trying to get into the spacecraft, he's not going to be able to do that by touching the spacecraft in this way. He's pushing the spacecraft away from him, right? And consequently, the spacecraft is going to push the astronauts away from it as well. Okay? And what we have to do, we have to finish that problem, right? Is all we have to do here, let's see, is just simplify those equations. In this, recall that in this problem, we use Newton's third law of motion to solve it. And we go, we have M2F. That's gonna go to the other right here. The negative sign. Okay. Note, see that this term here is gonna cancel out with this term here, right? I'm gonna highlight it. So in the next line, this term will no longer be there, but only this term right in here. Let's see if there's everything is okay, right? This M1 is going to cancel out with this M1. That's highlighted as well. And we're going to get exactly the same result that we got in part one. Okay, just by solving the problem in a different way. Don't forget to use, compare this answer here with this other answer here. I put a different notation, right? A sub x, but they are the same, f over m1 plus m2. In this case, we solve the problem in a different way. In this case, we solve the problem using Newton's third law of motion. And we also needed this other result here to solve for the acceleration in a different way. So that's one possible example that you're going to see, right? Let's take a look here. We are done with chapter on Newton's third law of motion now. Highlight it. Memorize, right? Let's laws of motion. Three laws of motion. I'm going to copy and paste those laws. You have to memorize them. There's no way to derive those laws mathematically. Okay, here's the second law. Second law of motion states the following. Okay, here you go. Laws of motion. That's the second law. I'm gonna get the first law. Newton's first law. Newton's first law, Newton's second law. Second law of motion. And then we have third law of motion. Okay. Newton's third law of motion. Comma, right? Shown. Sequence magnitudes. The first, the object one applies the object two is equal in magnitude and in opposite direction with respect to the force that object two applies to object one. Okay. And then we have that notation that I showed to you. That's shorthand notation. Force that one exerts on two. Okay. The above notation means the above notation Fij, okay, where Ij are numbers, integer numbers, means force that object I exerts, lowercase, exerts in object J. Okay, that's what this notation means. Going back here. Now let's take a quick look at those two chapters, okay? Here you go. Here are those are examples, equilibrium application of Newton's law of motion, okay? Equilibrium application means that the net force is equal to zero. So those are examples of Newton's first law of motion. Okay, acceleration equal to zero. Net force along the x-axis is zero. Net force around along the y-axis is zero as well. Okay, so here you go. That's one example, one kind of complicated example, right? That you want to keep the leg of your patient at rest, and you have this whole setup with pulleys and masses to ensure that the leg of your patient stay at rest, right? Orthopedists should know that. Here's another example. Okay, is a mechanic raising an engine, and we also have a pulley system here. An automobile engine has a weight W, right? Magnitude 3,150 newtons, which is around 315 kilograms. This engine is being positioned above an engine compartment. To position the engine, a worker is using a rope. Find the tension in the supporting cable and the tension T2 in the positioning rope. So there are two tensions here, and here is the weight. So what we are doing what you have right in here is the free body diagram of the forces applied to the engine alone. Okay. So here you go, another example. Okay, so a jet plane flying with a constant speed. Constant speed, acceleration is equal to 0, right? Here you go, here's the airplane. Constant speed, because it's going at constant speed, net force must be equal to 0. So we go ahead and look at the forces applied to this airplane. The weight is always there. The other forces I didn't mention to you before, okay? The other forces I didn't mention to you before, but I can introduce that to you right now. We have the thrust of the engine. That's the thrust of the engine. That's the friction, the air friction. R, air resistance, right? They call it air resistance, better. R. And this other force that you see right in here is called the lift. The lift in the wings of the airplane. The wings are shaped in such a way to provide a lifting force to the aircraft. That's why the aircraft ends up flying, okay? You have the wings, the wings of an airplane, any airplane, must be shaped in a specific way, okay, like an airfoil. So it can produce a lift in the airplane when the airplane reaches a determined speed. So what the guy is doing here is identifying all the forces, okay? And let's write down those new forces. I introduced you only to 4 forces, right? But there are more. Okay, let's write down the 4 forces here instead of looking for them. Forces. You know, the weight. 1, weight, always there. Unless you are in microgravity. Unless you are away from a planet or the sun, right? You still may be in a microgravity environment and still have a weight being subjected to the weight. Okay, let's see. Yeah, weight. The other force that I mentioned to you was the normal, right? Another force that I mentioned to you was the tension. And then we had the force of friction. And there are 2 forces of friction. 2 forces of friction. That's static friction and kinetic or dynamic friction. You're already familiar with those 4 forces. But like I said, there are more. The weight is the force of gravity, by the way. There in this example that you have in the book, you saw 3 additional forces. Thrust, thrust of an engine. Okay. And then you also have air resistance. Air resistance is also called air friction. Air resistance, air friction. Okay. If you are driving a freeway, you can experience this force, right? This air resistance force. All you have to do, accelerate your car to 50 miles an hour, 55, 60, 65, right? Whatever the speed limit is in the freeway. Open your window and stick your hand out of the window. You're going to see that a very strong wind coming towards your hand. That wind is in reality the air resistance. It's the force of air friction or air resistance. There is this other force that's called lift. Okay? Lift, the force that the wings of an airplane makes. Apply the force that the wings of an airplane. Okay, we can leave this way. The force the wings of an airplane, the wings apply. Okay, the wings apply to an airplane. Let's put it this way. In order to produce this force, the wings must be shaped in a particular way. Okay. Let me give you, let's see if we have an illustration here. Lift for wing of aircraft wing. Let's see, vertical, up and down. Lift is the vertical, can be either upwards or downwards, depending on the position of the airplane, acting on a wing, okay? The lift actually acts in the wing. And because the wing is attached to the airplane, the whole airframe of the aircraft is going to be subjected to this force. The focal point of this force is called the center. You don't have to worry about that. Let's see how an airplane, okay, right in here. Huh? Skip.
So we'll clear out all of this junk.
You can skip this video in 4, 3, 2, 1.
And then right next to that.
Skip.
Hello. So
Let's
today
see.
we're going to be taking a look at how planes actually fly. So basically, planes fly because they have wings. So thank you all very much for watching. No, seriously, this video is going to take a look at what the wings are actually doing, which causes a plane to fly. Now, I'm no physicist, so please forgive me if I say something out of turn during this video.
Okay,
So first,
here is the ideal shape of a wing, is that of an airfoil. It's kind of a water droplet. Okay, if you shape an object like that and you put it to move at a very high speed, right? Not very high speed, but at a certain speed. You don't even have to move it. You can just have a wind blowing through this airfoil. What's going to happen? The wing is going to have a higher pressure. The air is going to exert a higher pressure here at the bottom of the wing and a lower pressure at the top of the wing. Because the pressure here is going to be higher than at the top, there will be a net force, a net upward force. Okay? And that, you go, that's the air currents around the wing. Okay, which ends up producing a higher pressure at the bottom and a lower pressure at the top. And this pressure differential, see, low air pressure. This pressure differential results in a lift. Okay, that's how it works. So 3 more forces that you gotta know, and then there will be this other force that are, there is this gravitational force that we already learned. That's weight. The weight is a gravitational force with mg, but let's talk here about the gravitational force. Gravitational force. Okay. You already know that the weight is a force due to the Earth pulling you towards the center of the Earth. Okay. By the way, it's not just Earth that produces this force. Okay. If you go to the surface of the moon, to the surface of the moon, you will be subjected to a lower gravitational force. Okay, that's why astronauts seem to float. Not that they are floating; they're not floating on the moon surface. No, they're not floating. Seem, right? That's why astronauts seem to float on the moon surface. They're not floating. They are actually astronauts. They're not floating. They are not floating, they are actually falling towards the moon at a lower acceleration rate. Okay, which is g divided by 6, approximately 1/6 of the Earth's gravity. Okay, everything that has mass produces this gravitational force. Okay, everything, and I'm not kidding. It's everything, because the mass of the moon is lower than the mass of the Earth. Okay, its gravitational force and consequently the gravitational acceleration will be lower. Okay. Same thing applies to Mars. Okay. On the surface of this planet, your weight will be lower compared to that on Earth. To Mars and other planets, on the surface of a planet, your weight will be lower or greater compared to that of on Earth. Okay. And that's where we come to the point where I can start introducing a more genetic formula, which is also a law of physics. Same thing applies. Same thing applies. That is an equation that relates the gravitational force that a massive object exerts in another one. This equation is referred as the law of universal gravitation. Okay. Think about that. I didn't write down the law yet, but it's not difficult to memorize. Then we came to a point that we're going to need some figures here to illustrate. All right, in here. Any questions? Take advantage while I'm getting ready here to continue. Just think a little bit what I have told you, right? Universal gravitation. Okay, here you go. Okay. You already know that there is one simple, right? Simpler formula for the weight. You already know that, which is W equal to mg. However, this formula does not tell you the whole story. Okay, what does it mean? Instead, this formula is just an approximation to the more genetic equation. Okay, so the more genetic is like law of universal gravitation. Universal gravitation. If here you go. If weight, I'm gonna put that in vectorial fashion, okay? If weight is equal to mg, where g is a vector, and here I am writing that as being the gravitational force, right? Weight is equal to the gravitational force. By the way, this formula applies only to objects nearby the Earth's surface. Okay. Let's put that in a, I'm going to put that in a scalar fashion. Okay, here you go. So I don't scare you, right? Here you go. This formula applies only to objects nearby the Earth's surface. For objects further away, okay, a more genetic equation is given by, okay, and that comes to the point where I have to show you here an illustration. Consider two masses, try to picture that in your mind or even in the paper. Consider two masses, M1 and M2 apart, point masses. Consider 2 point masses, M1 and M2, further apart. Okay, and I'm going to get this drawing here for you in a moment. Yeah, okay, I got it. Illustration. So I put here law of universal gravitation. Law of universal gravitation. Okay? So consider two masses. Here I am 2 point masses. I'm displaying mass 1, M1. Okay, and in the next slide, I'm displaying mass M2. And those two masses are separated by a distance d, delta. Can be two planets, can be the Earth and the Moon. Okay, M2 is the Earth, M1 is the Moon, for instance. So what does the universal law of gravitation states? It states that the force in one, I would rather change this notation. Here you go. Force of two applied to one is better this way. Force of mass 2 applied to mass 1 is going to be an attractive force. Okay? According to Newton's third law of motion, the force that M1 applies to M2 is going to have the same magnitude, but opposite direction. Right? Can you picture that? And now I gotta put 1, 2. Force that 1 applies on 2. Okay? And now I gotta fix everything here. Force that 2 applies on 1. Yeah, okay, good. So those forces are attractive. Okay? That's the first thing that you have to know. And on the top of that, there's a relationship between this force, the mass, and the distance between the objects. Okay? Here you go. The magnitude of this force is going to be given by which, by the way, is a weight. I'm going to give you just the scalar. relation, okay? Going to be given by a constant that I call a constant G, okay? The mass 1, the mass 2, divide by a distance, by the square of the distance B. Okay? That is the scalar. Here you go. No negative there because I just writing down the magnitude of this force. Can you remember that? Whereas G here is a constant that was measured after this equation was formulated, okay? Here you go. Big G. Oh. In the above, G is the gravitational constant. Okay. M1 is, for instance, the mass of object 1, and M2 is the mass of object 2, like that. Oh, there's more, right? M1 is the mass of object 1, M2. What's going on here? Okay, my Word document here is low today. Okay, good. Is the mass of object 2, and D is the distance between the centers of the two objects, like that. Okay, so can you memorize that? Oh, and G, right? I'm gonna give you the value of G. Here you go. The value of G is, that's something that was measured after. The gravitation is the gravitational constant given by, there you go. Like that. M1 is the mass of object 1. M2 is the mass of object 2. And D is the distance between the centers of these two objects. Going back to the drawing. Here you go. The gravitational constant is always attractive between the two objects. Okay? Always attractive. And now, having said that, we may rewrite this equation in vectorial form. Okay, you can write here, right? Right, here you go. The weight I'm gonna get that. You know, let's see. I need this one here. M1, M2. Okay. And now I'm gonna change from D to something else that we call R, and I'm gonna change the, you know, distance from 1 to 2. Okay. So we can have a nice notation here, right? Where D is equal to this R12. like that. And by the way, here, what you have right in here is a unit vector R. I'm going to tell you, which is from 1 to 2, okay? And all of that is shown here in this illustration. Let's go there back here, right in here, you know? Here's force of 2 in 1, force of 1 in 2, right? And here is the vector that goes from the center of the object number 1 to the center of the object number 2, okay? Magnitude of this vector is equal to D, and here's the unit vector pointing away from object 1. That's the vectorial formula. But we must have this negative sign to ensure that the force ends up being attractive. Okay? And now I can erase that. But if you remember that the force is always attractive and the weight is given by this equation, you're good. You can solve your problems easily. Okay? And by the way, so we can do a simple example. Okay? Consider of 80 kilograms on the surface of the Earth. Okay? Find his weight, right? His weight using 1. The first formula that you got, mg, finding, and 2, the law of universal attraction. Universal gravity, right? Universal law of gravity. Gravitation. Universal law of gravitation. So 2 different ways of performing the same problem. Okay, so the first one is easier, right? All you have to do is to get his mass and multiply by g. You go, weight. Find the magnitude of his weight using mg, right? Mg is going to be 80 kilograms times 10 meters per second square, or 9.8, you can do that too. Now let's make it simpler, 800 newtons. And then we have the other possible solution. That's going to be of mass, m equal to, right? It's going to be, I'm going to get this one right in here. And now I'm going to change slightly my notation. Here's going to be the mass of the man. Here's going to be the mass of the Earth. And because this guy is standing on the surface of the Earth, it means that he's a distance big R from the center of the Earth, which corresponds to the radius where R is the radius of the Earth. Okay? And now what do we have to do? We have to apply those numeric values to this equation here. Okay, big G, we already know what it is. Here you go, big G is this value right here. Here you go. The mass of the man is going to be 80 kilograms, right? The mass of the Earth, we have to look in the book. We have to look in the book or in the internet, okay? Mass of the Earth, this document, mass of the Earth. Here you go. 6 times 10 to 24, right? Almost 6. 6 times 10 to 24 kilograms. And then we have to find out the radius of the Earth as well. Just checking the internet. You don't have to memorize that, but if you memorize this better, okay? Radius of the Earth. 6,371 kilometers. 6,371 million meters, right? 1 kilometer is 1,000 meters, consequently. And now you gotta do this math here to see what you get. But before, we do this math, let's simplify. Let's do as much simplification that we can. Kilogram, this kilogram, okay, these 2 kilograms here cancel out with this other one, with the kilogram square downstairs. Okay, this one goes away. This meter here cancels out with this other meter here. May feel like cumbersome, to do that, but that's what we are supposed to do. Let's see if I can do better than that. Yeah. Oh, we have one more meter here. No, I didn't cancel this one. Okay. I didn't cancel this meter, right? There must be something wrong here. Let's see. Oh, yeah, I forgot to raise the square here. Nobody knows that, right? Let's take a look. I forgot to raise the square there. Okay. And then when we raise the square here, we get something like that, and we get meter square as well. And this meter square cancel out with this other meter square that's here. And we end up with unit of force, that's the Newton, right? Meter square. Okay. And we can do this math. Let's see. Let's see here. I'm gonna put that here and this one right in here. And now I can. Okay. W, like that. Now let's do this numeric calculation. I'm gonna get the spreadsheet here. Okay. Equal 6.674. That's the difficult way of finding, right? The weight of object nearby the Earth's surface. E24, and then I have to divide by the square of 6,371,123. And let's see what we get. Hopefully, I'm not gonna crash my computer. Oh man, I'm getting 0 here. Okay, so I gotta do it in a different way. E4, wow, yeah. I see. Something wrong here. Let's see, 10 to 24, right? Okay, let's see if I get something back. Oh, okay. I got some. Okay, if you do this math, right? What am I getting here? 789. 789 newtons, right? Yeah, 789 newtons, which, by the way, is very close to that value of 800 newtons that I got. Yeah, which is approximately, I'm gonna put it here, approximately 800 newtons. Okay. So if I multiply 80 kilograms for 9.8, I will get a better result. It's going to be closer, 784, a little bit lower. 9.82, right? Should be 9.82. Let's see if I get it. 785.6. So from here to here, we get just what? 11 difference. So around 1% difference. 1% difference, right? And it is 10:05 right now. So let's take our break. But before the break, let's take attendance. Any questions about that? Today is lecture the 16th. Oh yeah, that's the lab today. That's here. Okay, I don't need that anymore. Good. Okay, let's start with Nuhamin. Are you there, Nuhamin? Taking attendance right now. Not in alphabetical order. I don't see Nuhamin here. Next is Matthew Aguirre Mata. I don't see Matthew either. Next is Jazzy Castellano. Thank you, Jazzy. Gabriel Contreras.
Here.
Thank you, Gabriel. Liliana Cortez.
Here.
Okay, thank you. Juan Escalera. Okay, Juan is not showing up for some time already, right? Next is Molly.
I'm here.
Thank you. Henry Kim. I don't see Henry here. Larell Williams. I don't see Larell either. Ruth Bandujano. I think I saw Ruth here. Okay. Noemi Martinez. Are you there, Noemi? Nope. Danae Miller.
I'm here.
Thank you. Ramon Olivares. I don't see Ramon. Taylor Forn.
I'm here.
Thank you. Stephanie Ramos.
I'm here, Professor.
Thank you. Jeremiah Reyes. Thank you, Jeremiah. Sean Rosario. I cannot hear you, Sean. I presume that your mic is not working. So just type there in the chat, okay? Let me, Jason Strait.
I'm here.
Thank you. Elena Trujillo. Elena T. Sean.
Here.
Thank you, Elena. Next is Jason Valadares.
Here.
Stephen Vathapali.
Here.
Thank you. Audrey Aguilar. Hello, Audrey. I can hear you, so let's put a star for now. Brianna Carrillo. Are you there, Brianna? Okay, I'm gonna put a star here for Brianna. Ali is standard. I see Ali here as well, and Alia Zavala. Thank you. And we have a total of this is a section. Okay, yeah, okay. So we have the right number of students, and it's 10:10 right now. It's a good time to stop and break from 10:10 a.m. to 10:25 a.m. And I see you in 15 minutes. I'm back here. Let's see, I got a message from Audrey, right? Get here to the attendance, and Audrey is here. What about Brianna Carrillo? Are you there, Brianna? Brianna and Ali is standard. Okay, now let's see. Ali and Val is here. Okay, so let's save that and what are we going to do now? We're going to do lab 3. It's going to be the first table. We usually do this experiment in the classroom so students can see that forces do add as though as they were vectors, okay? Is the demonstration of the vectorial nature of forces. And that's what this lab number 3 is all about. Okay, lab 3 force table. Let me upload your spreadsheet. Okay. Here, no. Let's take a look here. Google Drive. Okay, group 1. Lab 3. Oh, let me, before uploading, right? Let me check if everything is okay first. 6. Okay. Five. Three. 2. One. Okay, everything seems to be fine. And now let's get the spreadsheet lab 3 on group 1, lab 3 on the folder of group 2, lab 3 on the folder of group 3, 4, 4, 5, and 6. Now let's lab 3 right in here. Let's take a look here at this one. That's odd. Okay. Not supposed to be here. Okay. Okay, and we're gonna get another. Illustration courses, illustration E37 lab slides. Course table. Right in here. And okay, here you go. Here's I want to show you how the force table looks like. Okay. And I will walk you through the experiment force table experiment. Okay, so we have 3 videos here. Let's take a look. Let's take a look on this one here.
Novo Mela B3 Zero, menos 85% manchas. Previne o reaparecimento. Senti muitas dores e até hoje eu sinto.
Fale com seu médico sobre o herpes zoster.
Okay,
Ok.
here you go. That's how the first table looks like. Is a metal protractor graduated right here from 0 to 360 degrees. Okay, and it has a center here and a ring. This ring is attached to 3 cords, okay, which are pulled by masses that we hang from this pulley. Pulley 1, pulley 2, pulley 3, right? And here, you see this hanger here? This hanger, we add masses to this hanger to pull this string, this other string, and this other string. And we have to find the given masses 1 and 2. Let's say you put masses 1 and 2 here, and the angle, right, between those 2 masses. Find what would be the angle and the mass that would go in this other hanger. That's how it works. Okay, that's how this experiment is performed. The experiment is performed in the following way. Okay, the experiment is performed in the following way. Okay, given 2 masses pulling 2 different strings at a given angle, right? Find the mass and the angle required for a third force to cancel out the other 2 forces. Okay? That's what the goal of the experiment is. The goal of the, let's put it, the goal of the experiment is the following. Of the experiment is the following. Okay? Given 2 masses pulling 2 different strings at a given angle, find the mass and the angle required for a third force to cancel out the other 2 forces. Okay? And the equipment is that circular metal table, which is a protractor, a metal protractor that you saw in there. Ring with 3 strings. You saw the 3 strings there. Here you go. The ring with 1, 2, 3 strings. We are going to do this experiment with only 3 strings. This guy is doing that with 4, okay? With 4 strings. Let's see if we don't want to follow this one because you want to do it. He's doing that with 4 strings. Let's take a look at the other one. This one here. Yeah, right in here. Okay, here you go. 1, 2, 3 strings. 1, 2, 3 strings, and 3 masses. And they do exactly the way I'm doing it. They're making an angle of 90 degrees. Okay, and they're hanging the masses here, giving the mass and the angle between those 2 strings. Find the mass and the angle that a 3 force must be placed to cancel out the other 2 forces. That would be a demonstration of the vectorial nature of force. Okay? So if we look at my slide, so it's like that. It looks like that. We have the force table right here. I didn't put the numbers there because it would be too much work. The center of the table is right here. Those are the quadrants, 1, 2, 3, 4 quadrants. The pulleys that are placed at the edge of the table. You know, two of the pulleys are placed at an angle of 90 degrees. We're going to demonstrate the right angle triangle relation for those forces, okay? There you go. The strings are placed with the ring. The red line are the strings. Notice that those two forces are again at 90 degrees. You place the masses. If the masses are not canceling each other, are producing forces that do not cancel each other, the ring is going to be displaced from the center, right? Here's another situation in which this force here is not enough to counter the other two. But whenever we center the ring, here you go, here's the force 1, here's the force 2, and here's the, let's say, the force 3. That's the resultant of F1 and F2. Then we have, and the ring ends up being centered, then we have an equilibrium force here. And there will be a relation between mass 3, mass 1, and mass 2. Okay? That's how we perform this experiment. Let's take a look at the writing here. There are 1, 2, 3, 4 tables. Let's zoom in at them. Okay. Mass 1, we start with mass 1 that I choose to be 300 grams. Okay, don't forget we're using the same scale that we have used before, the scale with 100 of a gram resolution, right? Circular metal table, ring with 3 strings, 3 pulleys, 3 mass holders. The mass holders, they have 50 grams each. And then we're going to load more masses in this holder, into this holder. Clamp 1, pulley 1 is a 0 degree angle. Number 2 is a 90 degree angle. And then number 3 is anywhere opposite to the other 2 pulleys. Okay. Let's see here. Did I put the equipment list here? No, I didn't. Let me put that here. Equipment circular metal. I have to put it here. Here you go. Scale with a mass resolution of 0.01 grams, which is equal to 0.12345 kilograms. 1, 2, 3, 4, 5. Okay. The protractor, right? The protractor, the metal table. Let's take a look at the protractor here in this one.
Particular forces.
We cannot see the metal table. Let's see here. Yeah, we cannot see the protractor. Let's take a look at the other one. So you can see from the top. This one here. Propaganda. Okay, we can stop. Here you go. Take a look here at the protractor, right? The resolution in the angle is 1 degree. 40, 41, 42, 43, 44, 45, right? So we can put it here, protracting the metal table with a resolution of 1 degree. Superscript right here. You need those two pieces of information to get the right significant figures. Get the right number of significant figures. Okay, so I have chosen 300 grams here for one force. The other force, oh, that's the angle theta. Angle theta, I put it at 0 degrees, right? Angle theta 2, I put it at 90 degrees. And then I came up with what, 200 grams, 300 grams, 250, 300, 350, 400, 450. Make sure that you put them with the right number of significant figures. And when we perform the experiment, what do? I find a lower bound for the masses that we still have equilibrium. Because of friction in the experiment, you are not going to get one sharp value for the third mass. You're going to get a range of masses. You know, the lower value and the upper value. Okay? The difference is not much. Let's see. Let's see what the difference is. 350.3, right? And this other one is 370. Roughly 20 grams. 20 grams out of 350. Let's see here. 20 grams out of 350 is how much percent? It's 5% difference. 5% range. Okay? 6%. 5.7%. Not bad. Okay, so when we perform, we get this lower and upper value for the masses and this angle here. In this case, it's 215, the other is 221, and so on, okay? And then, what is the theory behind this experiment? Okay, I already explained that to you, right? F1 squared plus F2 squared must be equal to the resultant force, the square root, right? The square root of the sum of the squares, it must be equal to this resultant force. And then we perform the experiment, right? So the situation goes like that. You know, the force, here you go, Pythagorean theorem, right? Oh, I'm sorry, protractor resolution is half degree. We use a half degree protractor, different from that one. Okay, half degree. No, not this one. It's right here. This one here. Okay, and the scale. Now, here you go. Here's the equation that we need. Pythagorean theorem. Pythagorean theorem because we are using two masses, two forces at an angle of 90 degrees. Okay, and when we substitute mg, right, for all those two forces, the g cancels out. And we get this relationship between the masses. Okay? This experiment can get a range of value for M3 due to friction, right? M3 lower and M3 upper. Plot the M3 square average along the y-axis, and that's what our spreadsheet have done. Okay. M3 average. Then we square, take the average of those two, then we square, get this value here. Along the y-axis, and the M2 average square along the x-axis. Well, it's not average here, it's just M2 square. Well, here, it is the M2 that we are varying, right? See, the M2 that we are varying, the M1 remains the same. That's how the experiment is performed. So we plot M3 average square against M2 average, M2 square. And then if we do that, we are supposed to get, this guy is a constant, right? 0.3 square. That's the one that we are using. We're supposed to get a slope equal to 1 and an intercept equal to m1 squared. That's what the Pythagorean theorem expects, right? That's what the Pythagorean theorem spells out here. Okay, there is another relation too. Is the m2 over m1. M2 over m1 should be the angle theta 3. Okay, so going back to my drawings here, right? To the drawings here. M2 over M what? M2 over M1. M2 over M1, that should be the angle theta. This should be theta 3. Okay? Theta 3 for this force that you see there. So, that's what the theory predicts, right? So we have, if I call this one X and this one the Y, we can plot tangent of theta along the y-axis and m2 divided by m1 along the x-axis. Okay? So we have two plots. Plot two graphs. Right? What graph is going to be m3 average along the y-axis, m2 square along the x-axis? Two graphs. No, I don't like that. Okay, A and B. Okay, the tangent of theta 3 along the y-axis. Along the y-axis, m2 over m1 along the x-axis. Slope, in the first case, this slope should be 1. Intercept should be m1 squared. Okay. In this case, the slope should be 1. That's all we need. So can you do that? Let's start with that. Start by plotting those two graphs. Log the slope and intercept on the last table to obtain the percentage difference. Log all units. Right? Display the proper number of significant figures. Fill up the regression equation R square. Find the CL. Those are the steps that you have to do. Do you understand here the theory behind? Okay. So we're performing an experiment that's independent of the theory. And if you get a small percentage difference, we are corroborating the theory. Okay. So let's go here one by one, see how you're doing. The first thing I wanted to know is whether you download the graph, download the spreadsheet, download, right? Nuhamin, is Nuhamin there? I don't see Nuhamin. Matthew, are you there, Matthew? I don't see Matthew either. Jazzy, did you manage to download the spreadsheet, Jazzy? Yes, okay, good. So Jazzy has her spreadsheet. Gabrielle, did you manage to download the spreadsheet, Gabrielle? Hello, Gabrielle. Okay, Gabrielle is not answering.
I'm working on it.
Are you working on that? Okay, so you're working on downloading the spreadsheet, right?
Yes.
Okay, so let's see. Liliana, did you manage to download the spreadsheet?
Yes.
Okay, I'll get to you, Audrey. Let's see. Next is Juan Escalera. I don't see Juan Escalera here, right? Gabriela. Okay, Gabriel managed to get the spreadsheet downloaded. Molly, did you manage to download the spreadsheet?
Yes.
Okay. Henry Kim, did you manage to download the spreadsheet, Henry? Let me see. I can't hear for Henry. I'm gonna put a star here in his, and put the O right in here for now. Larell is not here. Ruth, are you there, Ruth? Ruth is not here. Noemi? I don't see Noemi either. Danae?
Yes, I downloaded.
Okay, thank you. Ramon Olivares? Ramon is not here. Taylor? Born, did you manage to download the spreadsheet, Taylor?
Yes.
Okay, next is Stephanie. Did you manage to download the spreadsheet?
I'm still doing it.
I didn't understand. What did you say, Stephanie?
Oh, I'm trying to download it.
I should download. You're working on the download. Okay. Jeremiah, did you manage to download the spreadsheet? Hello, Jeremiah. Yes, okay, good. Sean, did you manage to download the spreadsheet, Sean?
Yes.
Okay, good. Jason?
Yeah.
Okay, next is Elena.
Yeah, I downloaded it already.
Okay, thank you. Elena, next is Jason Valadares.
Yeah, I got it.
Okay, good. Stephen Hapali, did you manage to download it? Good, thank you, Stephen. Audrey, managed to download, right? Okay, now what about Brianna? Are you there, Brianna? Did you manage to download? Okay, good. Now Brianna is here. Okay, next is gonna be Ali. Are you there, Ali? I don't see Ali here in my list anymore. Standard. By the way, everybody has a group, right? And then you have Alia, Zavala. Okay, thank you. Good. Now we have 18. Henry, 16, 17. Who was not called, by the way? Okay, everybody was called. Okay, good. So after download, you need to plot two graphs. Two graphs. Okay. So just to refresh your memory, the first graph, that's the first graph. Let's see, here you go, two graphs. That's the first graph. That's the second graph. I'll give you some time to plot the graphs. This one here versus this one here, right? And the other one here. J16. Group 1 has only 2 students, right? Let's see who else. Group 2 apparently has 2 students only. Unless Henry makes himself known. Are you there? Are you there, Henry? Okay, get here from Henry. Let's see, group 3. How many students group 3 has? Only 1 student. Danae, you're alone there in the group, right?
Yeah.
Okay. Wanna join another group, or you can do it by yourself? Can handle by yourself?
I think I'm good right now.
Okay, good. So group 4 had 4 students. Group 5 has 4 students. Group 6 has 3 students. Okay, just the top groups have few students. Now let's. Did you manage to plot the 2 graphs, Jesse? If you didn't manage to plot, just say I'm working on that. You're not going to be punished for that. Okay. I can't hear from Jazzy. Let's go to the next one. Here go. Oh, Gabrielle, did you manage to plot the 2 graphs, Gabrielle, or it's too early?
Too early. I'm still working on it.
Okay, it's still working, right? So let's wait a little bit longer. I'm gonna plot my graphs here. M3 square average, M2 square, right? Insert. See, those are real life experimental data, okay? So they kind of lined up in a straight line, right? Let's see if you get the slope of 1. Yeah, it's very close to 1. 9.94, right? Almost 0.94. So you're talking about 6% difference only. Supposed to be 1. The intercept is 0.0917, which is very close to the square of 0.3. So you can see how good the data is. It's not that how good the data is, it's how good the theory is, right? The theory reflects real life. And here's the other
Plus, I have
one.
a question.
Yeah.
For MacBooks, or yeah, do we press command, right?
You mean to plot the graphs?
Yes.
Okay, so you highlighted. Are you using a Mac or a PC?
A Mac.
A Mac, okay. In the case of the Mac, you're going to highlight this one here. You press the command key, and then you highlight M2 square, okay?
Yeah, because it's not letting me like copy it.
Oh, it doesn't let you. Oh, that's too bad. But did you try it? You know, the command key. The command key is just like that. Let's see.
Yeah, I know where the command key is. It's just it's not letting me.
Does not let you? Okay, let me answer Audrey. Audrey, you press the control key in the PC, okay? In the PC, you press the control key to highlight the second column. What's your name? The one that you're having problems there?
Gabrielle.
Gabrielle. Okay, Gabrielle. Let's see if we can have another way of doing that. Let's do it another way. Okay? Look, we're gonna, since you're having problems, highlight those two columns here. Okay? Let's highlight those two columns. Okay, and then you plot. It's not the correct one, but we are going to, we are going to fix it. Okay, we're going to fix it. Now, did you notice that those two columns become highlighted? See that when we plot the graph, right? Do you see that? Okay. Do you see that in your Mac?
Yes.
Okay. Now what do? You go ahead, go to the edge of this table here. See that? When it highlights, you click it and drag. And now you have the right plot. Make sense? That's a little trick that we use to cheat the computer.
Show me one more time. Sorry.
Huh?
Can you show me one more time, please?
Yeah. Okay. So you're going to do the following. You're going to plot the incorrect graph initially. You know, those two columns. Make sure you can highlight those two columns at the same time, right?
Mm-hmm.
Insert, plot, right? Here you go. We have the graph, the incorrect graph plotted. Okay, and now we are going to fix that. Notice that the two columns become highlighted when we, click the graph, right? So what are you going to do? You're gonna get this column here, the incorrect one. You're going to click and drag, and now you have the right graph. That's a little trick that we can do to plot the right graph if your command key is not working, okay? Your command key was supposed to be working.
I'll try one more time. Thank you.
Did it work?
No, but I think it's just something wrong with my computer right now.
Mm-hmm. Well, you can share your screen later on, so we can figure out what's going on. And you can also interface your group members, seeing if they're being successful. Okay. Liliana, did you manage?
Yes, I was able to plot.
Oh, the two graphs. That's good. And next is Molly. Did you manage to plot the two graphs? I cannot hear you, Molly. Okay, I'm going to put a little wall here for Molly. Henry, are you there, Henry?
Yes, I am.
Okay. So did you plot the two graphs?
Yes,
Henry?
yes, I did.
You did? Okay. So the next question is that I'm going to ask you, what's the slope, right? What's the slope that you got there in your graph?
Slow. A second.
First, you have to get the graph, right? Then you have to find the regression equation. The slope of the first graph. Okay, so work on that. I'll get back to you. Okay. So let's see. I'm gonna say that you're working on that. Then Laurel is not here, right? Let's see. Next, Danae. Did you manage to plot the two graphs, Danae?
Yes, I plotted them, but now I'm trying to pull up the I got the trend line, but I'm trying to pull up the equations, like the slope equations for it.
Okay. Do you know how to do that?
Can you show me how to do that again?
Yeah, let's do that. Let's go back to our graph, the one I was using. Here you go. Here's my graph, right? You're at this
Mhm.
point. Okay, you're gonna click one of the data points. All the data points are going to be highlighted.
Uh-huh.
Going to right click at one of the data points. You have this drop down window, and then you're gonna highlight add trend line. Add trend line, linear.
Okay, and that should pop up on the side. Okay.
Yeah, display equation chart, display R square value on chart.
Okay. Thank you.
Okay. So notice that I'm getting like 6% difference only. So let's see here. Danae working on the first slope. Ramon is not here, right? Next is Taylor. Taylor Thorne. Did you plot the two graphs?
Yeah. Yeah.
Okay, what's the slope of the first graph?
We got 0.91.
0.91. Okay. What is the intercept of the first graph?
0.0887.
0.0887. Very close to 0.09, right? Very close. That's good. And what is the slope of the second graph?
0.939.
Second, 0.939. 0.939. Okay, good. 1%, no, not 1%. That's more like 6% difference. 6% difference here. Here the difference is very small. Here is 9% difference. Okay, good. So now you should start working on the units, right? And the significant figures. Let's go for Stephanie now. Stephanie, are you there?
Yes, I'm still like I already graphed the first draft, but I'm still struggling like to find the slope for it.
Okay, so you did graph the
The first one.
but not the second, right?
No, I'm about to do the second one, but I just want to make sure I have the slope for it.
Okay, so let's see. Do you have at least the slope of the first graph, the intersect of this first graph?
No.
No? Okay, so you're still working. Okay, I'll get back to you later on. Let's go now for Jeremiah. Hello, Jeremiah. Okay, so here you go. Jeremiah is not answering. Let's go for Sha.
I also have a 0.91.
0 point. Okay, you have the same. You're in the same group. Consequently, you have the same slope, right?
Yes.
What about the intercept? Should be. Do you get
0.0887.
Oh, 887. Okay, 0.887. Okay. Oops, 887. Okay, which is 0.89, right? For 0.089, rounded up. And what about the slope of the second one? What did you get?
0.939.
Okay, 0.939. Same as Taylor. Okay. Okay, and next, and then they work, just start working on the units, right? Units and sig figs. Sig figs. Jason, are you there, Jason?
Yes.
Okay, did you plot the two graphs?
Yes, I did.
Okay, good. What's the slope of the first graph that you got?
The first graph, I got 1.0262.
Okay, 1.0262. Okay, so you're getting 3% difference only, less than 3% difference. What about the intercept of the first graph?
I don't think I caught how you're supposed to get that because my graph doesn't intersect with the y-axis. It's just in the middle of it.
Okay,
Can you?
so let's go there. This one here, right? Okay, See, do you get a regression equation like that?
Oh wait. Oh, I just sorry, I forgot how to do like algebraic graphing. My y-intercept. Let me read that to you. I'm
That,
sorry, I forgot what the
yeah,
plus part was.
that's the slope, right? This one is the slope, and this
Yes.
one here is the intercept.
Yes, sorry. My brain's a little scrambled. My intercept was 0.0911.
0.911. Okay, very close to 0.09. That's what the theory tells us. Okay, and the slope of the second graph?
My second graph, the slope was 0.9753.
Okay, good. Very close to 1, 2. That's 2.5%. Okay, and now I'll work on the units and sig figs, okay? It's 11:15. Let's take a break. My throat is starting to get dry. Need to drink something. And when we return, we continue with Elena, right? And get the, here you go, break from 11:15 a.m. to 11:30 a.m. Okay, so I see you in 15 minutes. I'm back here. Now we are going to talk to Elena Trujillo, right? Elena, did you manage to plot the graphs?
Yeah, I did.
Okay, good. Did you get the same slope? Let me see, that's the right one. No, I'm looking at the wrong one here. It's this one right in here, Elena Trujillo. Yes, do you get the same slopes and intercept that Jason got?
So for the first one, the slope I got 1.03,
Okay.
and then the y-intercept I got 0.0911.
Mm-hmm.
And then for my second graph, I got the slope is 0.75.
Is it 7.5? 9.75, right? Or 7.5?
975.
Okay, okay. Yeah, just like Jason, right? Okay. Okay, so now you can start working on the units and sig figs. It's 11:30 now. We still have half hour to go. Jason Valadares. Did you plot
I'm still working on it.
working on the two graphs?
Yeah.
Okay. So let's go for Stephen. Did you plot the two graphs, Stephen?
Yeah. I got the same as Elena.
Okay, so let's see. Let me just copy and paste here, right? There you go. That's good. And now you can start working on the rest, right? This units and sig figs. Audrey, did you manage to plot the graphs? Well, Audrey was having a problem with her computer, right? Let's see, Audrey. Yeah, okay, Audrey is not listed here. Okay, so computer problems, let me put here. Computer problems. Next, Brianna Carrillo. Did you manage to plot the two graphs, Brianna? Let's see here. I'm still trying to graph them. Okay, it's two working. Brianna and Jeremiah. Let's see. The slopes for R were identical to Sean's. Let me see. Let me see, Jeremiah, right in here. Okay, and Sean. They are okay. You two are in the same group, so that's acceptable, right? Okay, so here you go.
We're on the same group. We all got the same thing.
Who was that?
I'm Stephanie, but we're on the same group and we got the same thing, the same value.
One minute, let me see. Stephanie Ramos?
Yes.
Okay. So did you plot the two graphs, Stephanie?
Yeah. We ended up
Okay.
getting the same thing. Yeah.
And you got the same values as the other students, right?
Yes.
Okay, good. So here you go. Now let's go back to Brianna is working. What about Ali? Ali Standard. Did you manage to plot the two graphs, Ali? We're having a thunderstorm there outside and we don't have electricity here. So if you notice it, but I'm still talking to you because I'm using that device, right? The UPS device, uninterrupted power system. So hopefully it's gonna last long enough to finish for the next half an hour. But let's see. Ali, are you there, Ali? Ali, I don't hear from Ali. So
Yeah, I'm here. I'm here.
Okay. You managed to download the graphs, Ali?
Yeah, I've downloaded it.
Yeah, not the graph, the spreadsheet, right? You managed to plot the graph now, the two graphs.
No.
No, you're working on that? Okay.
Yeah.
Okay, make sure you can finish before 12 noon, okay? Now, Alia Zavala. Are you there, Alia?
Yeah.
Did you manage to plot the two graphs?
Yes.
Oh, okay. So what did you get for the first slope?
I got 0.9893.
Okay, that's very close to 1. That's good. And what about the intercept of the first graph?
It's 0.0917.
0.09. What else?
Yeah, 0.0917.
17. Okay, that's good too, because it's very close to 0.009. 0.09. Okay. The slope of the second graph?
That's 0.9632.
0.9632. Okay. Okay, so it's less than 4% difference from the value that we expected. Okay, so this data seems to be very good. And now you can move on to the units and sig figs. Okay. And let's go back to group number 1. Nohamin. Okay, Nohamin is not here, right? Nohamin is not here. Next is Matthew. Matthew is not here either. What about Jazzy? Okay, working? Okay, working on the graphs, on the two graphs? Okay, good. So let's go for Gabrielle. Did you manage to finish the two graphs, Gabrielle? Gabrielle Contreras. Yeah, Gabrielle was having a problem with her computer too, right? Yeah, she restarted her computer. Okay, restarted computer. Next is gonna be Liliana Cortez. Did you get the slope of the first graph, Liliana?
Yes, I got 1.121.
121. Okay, good. That's 12% off the actual value. Okay. What about the intercept of the first graph?
I got 0.105.
0.105. Oh, yeah, not bad. Huh? It's very close to 0.09. 0.09 is 5% off. 5% off. Not bad. Maybe 10% off. Yeah. Supposed to be 0.09. Let's see how much percent is it off. 0.09 divided by this one here. And then we get, and I still have to subtract from 1, 14% off. There are 14% off. Okay, what about the slope of the second graph?
I got 0.933.
Okay, that's 7% off. That's good. Okay, now work on the rest. Okay, and let's move on here. Juan Escalera, are you there? Nope. Juan Escalera doesn't seem to be here. What about Molly? Did you plot the two graphs, Molly?
I have.
You said yes?
Yes.
Okay, good. What is the first slope? The slope of the first graph?
I got 1.121.
121, just like Liliana, right? Okay, they're the same group, so should have the same. What about the intersection of the first graph and the slope? You get the same values for as Liliana did?
Yeah, I got the same thing, 0.105 and then 0.933.
Okay, good. So, and thank you. So let's go for Henry. Henry, are you there? I don't see Henry in my list. Okay, let's see here. Oh, right. Laurel is not here. Laurel and Ruth Manduhano. No, Ruth is not here either. The other one is Noemi. I don't see Noemi. Now, Danae, did you manage to get the slope of the first graph?
I think so, but yeah, we're gonna see. I don't like my percentage difference.
Oh, okay. What did you get for the slope of the first?
So for the slope of the first one, I got 0.7162.
0.7162?
Yeah.
Like that? Oh, it's a little bit off, right? Let's see your group number 3. Let's see what's going on here. Group number 3. Yeah, that shows like 20, almost 70% difference, almost 30% difference. A little bit suspicious. Let's see what's going on.
Yeah.
Let's see. Why is not okay? Good. So that was this group number 3, which is you, which you are part of. The name group number 3. Good. Move it here, and I'm gonna plot same graph that you plot, right? M3 square. M2 square. Insert. Let's see. That's seems like a straight line. Let's see. I'm getting to the same thing. Okay, so the problem is the data, not you, right?
Okay, good.
Yeah, the problem is the data. So I'm surprised that, let's see if Let me see if I can get something better than that.
Because my second one's not pretty either.
Let's see. This one here. What did you say?
My second one is a high percentage as well. So.
Let's see, higher. Must be those two here. Yeah, if I eliminate those 2 points, I still get a high. I still get a high percentage difference. So yeah, if we were in the classroom, I would be asking my students to repeat this experiment. Okay. So let's take a look at the other one. This other graph here. Did you get? Oh, wait a minute. I want to know the intercept.
It was 0.1048.
0.10. Okay, the intercept seems to be better. 0.103.
Yeah, it's better, but still pretty high.
0.10. Yeah. Yeah, the intercept is better. Yeah.
1048.
1048.
Yeah.
And what about the slope of the second graph?
So my slope for the second was 0.8382.
0.8382. Okay, 0.8382 is 17%, 16% difference. Okay. Yeah, which is okay. Okay. So you can continue doing the rest, right? Units plus significant figures. And Ramon Olivares is not here. Looks like I went through most of you. Let's see. Jason Valadares. Did you manage to finish the plot of the graphs?
Yeah, I finished the second plot.
Okay. And did you get the slopes and the intercept?
Yeah, but for some reason I got a different number, so I'm not sure if I'm highlighting the proper columns on the second table. But for my slope, I got, let me see if I can zoom in, 1.0262, and the intercept is 0.0911.
0.0911. Okay, what about the other one?
So that was the second one. The first one, which columns did I have to highlight again?
There are two graphs, right?
Yes, the first graph, that's the one I wasn't sure about. Which one, which two columns did I have to highlight to create the scatter plot?
Okay, for the second graph, you have to, let me go here. Okay, it's those two columns, tangent and the M2 divided by M1.
Oh, I see. Okay, I got the ones. Okay, and then double check what about for the first table?
For the first table, okay, the first table is right in here. This one, M3 average square, M2 square.
Oh, okay, I see. So if that's the case, then I guess I got confused between the tables. So in the first table, the numbers I gave you would be for the first graph, and the second one I'll work on right now.
Yeah. See, you can also see that you're getting the same slopes as your classmates, okay?
Okay, got it.
You know, yeah, 1.0262 is just approximately 1.03. So you're in good shape.
Got it. Thanks.
Okay. So let's see. Audrey, are you back, Audrey? No, let's see. And Brianna? Last time we talked, you were working on the two graphs, right, Brianna? Did you manage to finish them? I don't hear from Brianna, although she's here. Let's see. Let me put a little O here for now. And Ali. Hello, Ali, are you there? Did you finish your two graphs?
Yeah, I'm here. I'm not done yet. My service is just really slow, so I'm just trying to work on it. Yeah.
Okay, so I'm going to put it here working. Work on the graph. Okay. So Jazzy is here. Okay, do you folks have any questions? We have 10 more minutes to go. Like I said, I don't have any electricity here at home, but I'm still going talking to you. Thanks God my UPS devices here. They're not beeping yet. But if somehow I lose contact with you, must be because I run out of electricity here from my UPS, right? Uninterrupted power supply, right? UPS uninterrupted power supply. And let's see, Jesse, are you there, Jesse? Oh, working on it, okay. Well, I think you, let's see, one more. Should there be 5 decimal places in the unit? Let me see, for table 4-1, let's take a look at there. Table 4-1. Where? But you gotta tell me, Molly, for the mass. Okay. For the mass, that's right. It should be there 5 decimal places. That's right, because those are masses, right? And the units should be kilograms. How do we get the units for what? For the mass or for the angle? Okay. Elena is asking me, how do you get the units? Which for both? So you're referring to the first table, right? To this table here, right? Elena? Okay, yeah, for the mass is kilogram, right? See that? For the mass is kilogram. So the same unit that you use here, you gotta use here, here, and here, right? And for the angle, we are measuring degrees. That's why I put degrees here, the symbol of degree. Okay. So again, the same unit that you have here, you must have here and here. Okay. And don't forget the unit here for m2 square, right? M2 square, the unit should be what? You know? And here too, M3 average square, what would be the unit? Okay. Yeah. And then here, the unit here is kilogram divided by kilogram, right? So you gotta put the unit for this ratio. Well, think about that. M2 has a unit of kilogram, right? M1 has a unit of kilogram. Kilogram divided by kilogram, what do you get? If you divide, you know? Yeah, they would cancel. And then you get what? One thing divided by the one thing. The same thing divided by the same thing, right? Is equal to? Yeah, no unit, that's right. But you display the unit with the number 1. Kilogram divided by kilogram is 1. Okay? So you write that down 1. And the number 1 means that there is no unit. Okay, 8 more minutes to go. Okay, so if you don't have anything else, I think we can stop now. And I see you again on Monday, right? I will stay here for the next 8 minutes. If you want to ask any questions, and then otherwise, see you on Monday. Thank you for being here.
Professor,
Yeah.
I have a question about the second lab.
Uh-huh.
So my group is trying to figure out the units for the graph in the second lab.
Okay.
In the 2-3 table.
Okay.
I was just
let me get the which group are you?
Group 5.
Group 5, lab 2. Group 5, lab 2. Let's see here. And which table you said?
It was the 2-3 table.
2-3. Okay, good. So this one here, right?
Yes.
Okay. So what the units for T?
Hold on. Let me. I kind of forgot what the T represents. I'm sorry.
T represents time. How long the cart took to pass the photo gate. What's the unit of time?
It would be seconds, I believe.
Yeah, that's right. It should be the regular SI units, right? What about X? What does X represent?
Oh man, I wish I wrote down the notes for that. I don't remember what each one represents. I'm sorry.
Okay, so you gotta go back to your notes, right? Let's take a look here. Open. I'm gonna open here first. Let's see, browse. Accelerated motion, right in here. Okay, so here you go. I showed you this, right? Those illustrations, right? Here you go. Here's the cart, and see that? See the capital X here, and see the lowercase x here. Capital X is the position of the front bumper of the cart. Okay. What's the unit for position?
So units would be, I'm assuming, meters?
Yeah, okay, yeah. And then that's the second. What about the other? Let's see. Lab 2, right? D, what's D, right? D is the difference between X and Y, okay? Is the difference between X and Y. What's the unit for something like that?
That would still be meters, correct?
Okay. What about the V? V is what? Is L, here you go, L divided by T, right? L is length and T is time. What's the unit for V?
It was velocity, correct?
Yeah, velocity.
Okay. And that's meters per second?
Yeah, and then you have V square. V square is the square of the previous one, right? What's gonna be the unit for V square?
Meters squared, second squared? Wait.
Yeah, that's right.
Oh, yeah?
Yeah,
So M squared over S squared, it would be?
That's right.
Okay. Awesome. I believe that's it for me then. If any of my group mates are still in here, if they have questions, they can go ahead.
Yeah, I have one question. So for table 5, so 2-5 in the same lab, would you want the unit in meters as well?
Let's see. Yeah, everything is a mixture of the main significant figure, the main units of the SI system, right?
Okay,
so
got it.
slope. Slope is going to be the unit of the rise divided by the unit of the run. Okay. A is acceleration, right? G
So that
is
would be
also,
meters per second square, right?
yeah. G is also acceleration, right?
Oh, okay.
And this delta here is a percentage. It's a percentage difference. So you just put the, oops, You just put the symbol of percentage as a unit. Okay? Percentage is the unit. Okay?
Got it.
Anybody else? All of that is Jason, all of that is. This group. Okay, and Molly, are you there? Are you still there? No, Molly left. Okay.
Okay, thank you, Professor. Have a good weekend.
You too.
Hey, Professor.
Yeah, hi, how are you doing? Danae?
I'm doing okay. So I'm just checking up on for this lab, my units for the slope and percent difference and intercept.
Okay.
So for the percent differences, it's just a percent, right?
Yeah, you just the symbol, just use the symbol of percentage.
Okay.
The percentage, where is that? The percentage unit. Yeah, percentage difference right in here. Units.
Okay.
Right in here too, here and here. Those three cells.
And then for this, okay, wait. So it'll be slope is what, y over x, correct?
Slope, is rise divided by the run.
Rise by the run.
Yeah. If you're talking about the units, right, of the slope, it's going to be the units of the rise divided by the unit of the run.
So it'll be 1, right? Because m squared. M squared.
Let me see. M squared. Yeah, that's right. It would be 1. Are you talking about the units, right? The unit of the slope.
For the first one.
Yeah, this one here. Yeah, would be 1. Would be unitless, right? So you put the
unitless. So I put 1, right?
Unitless unit. So you just write down 1, the number 1.
Okay. And then for the intercept, it's the y-intercept. So whatever that one is, so it'll be meters squared, right?
Yeah.
Okay. And then the last one, slope, same thing, but it was in this case. Oh shoot. Would tangent theta? I don't know what to do with the tangent. Is it still rise over run?
Yes. What's the unit of the tangent? First, you gotta know what the
Is
unit
it
of
in degrees?
No, degrees is the theta, right? The theta is in degrees. Okay. But the tangent has no units either. Okay.
It has no units.
Yeah, it should be just 1. Okay.
So it'll be 1. So it'll just be the x axis. So it'll be 1.
Yeah. Unit is a unitless unit.
That's unitless. Okay.
Yeah.
Okay. Thank you, Professor.
Okay.
Oh, last thing. So for my confidence levels.
Yeah.
When we write it out, we type out the number that is on the 6th row, right? Because I know the n is 6. Y is the y-intercept, correct?
Y, no. Y is the equation. Okay.
Oh, the whole equation.
Yeah, the whole equation.
Oh, duh. Okay.
The equation for this one, the equation for the first graph, the equation for the second graph. Okay.
Okay. But for my confidence levels, so I type out the 0.994840 for a minimum.
No. No, you gotta
What do
go.
I
You
what
gotta
do
go
I
in
put
the
in?
table. You gotta go in the table, right? Let's go there to the table.
Uh-huh.
That number that you told me should be the R square, not the confidence level.
My R
Okay.
squared is 0.9955.
Okay. And the other number, where did you get the other number?
I got it from the confidence level.
Hmm.
So I knew my R squared lied in between, right?
Yeah. So here, 6, right? 6 data
6.
points, right? That's
Yes.
the row. What's your R square again?
9955.
9955. Okay, 9955 is between those two values, right?
And I put those values or
Between those two values, right?
yeah.
Okay, so your confidence level is here at this row. See that?
So I look at that level. Okay.
Okay, so you gotta go up there, right? So your confidence level, the lower bound is gonna be this one, and the upper bound is gonna be this one here.
Okay.
Okay.
Okay, thank you.
And when you type that, don't forget to put equal 1 minus 10 to minus 5, right? Equal 1 minus 10 to minus 6.
1 minus 10 to okay, the equals. Okay.
Yeah, don't forget to put the equal. No?
Okay.
There you
All
go.
right. That's it. Thank you.
Welcome. Anybody else?